Welcome back to the Deep Dive. Today, we are wrestling with a question that I think sits right at the cutting edge of cognitive science and AI.
Oh, absolutely.
And that question is, do deep neural networks actually see the world? Or are they just performing these incredibly complex statistical calculations that,
Yeah.
that just mimic vision?
It's the $64,000 question, really. Because if you look at it just quantitatively, the machines have, well, they've won.
They've won, yeah.
I mean, think about the revolution in computer vision that kicked off around 2012 with AlexNet. The success has just been overwhelming.
It fundamentally shifted the goalposts.
Yeah.
Before these powerful deep neural networks, or DNNs, the error rate for identifying objects in challenges like ImageNet was stubbornly high.
Right, around 26%.
Exactly.
Yeah.
And now state-of-the-art models are, what, routinely below 1% error? It's just a miracle of prediction.
And that success comes from what these DNNs fundamentally are. They're massive, nonlinear function approximators. They learn the mapping between the input, the millions of pixels in an image, and the output, the label school bus or cat, just by adjusting millions of parameters.
Across huge data sets.
Across huge data sets, they are magnificent at correlation.
But that's the key, isn't it? Correlation is not causation, and prediction is not perception.
Precisely.
So our mission today is to dive deep into the sources that compare the behavioral mechanisms of human sight against these, near-perfect machines.
Right.
We need to find out where the processes diverge.
And what that tells us about how we actually see. And, before we even get into those behavioral gaps, we have to set the framework for the whole conversation.
Okay.
And that's the distinction between a tool and a model.
A tool versus a model.
Yeah. DNNs are incredible scientific tools. They help biologists predict protein folding. They accelerate climate simulations. But being a useful means to an end is totally distinct from being a scientific model.
Which is a concrete, testable hypothesis about how a natural system actually functions.
Exactly. We're asking if they truly model human vision, not just if they're useful.
That's a great distinction. So let's start on the human side of that equation and clarify the bedrock of sight, the difference between sensation and perception.
It might seem basic, but its implications for AI are profound.
So sensation is the low-level stuff.
It's the low-level neurological event. It's detection. It's transduction. When light hits your eye, the rods and cones convert that light energy into an electrical impulse. That's sensation.
Just the raw data capture.
The raw data capture. Whether it's light in your eye or sound waves hitting hair cells in your ear, it's all just sensation.
And so if that's the detection, then perception is the interpretation.
Precisely. Perception is the higher brain function that integrates all that raw data with context, with memory, with your experience to create a mental construct.
So sensation registers a wavelength of light.
And perception tells you, I see a green car parked across the street. That's the integrative step where meaning gets made.
Right. And the sources gave us a classic way to quantify the limits of our sensation, which is Weber's law. Why is this so relevant here?
Weber's law is fundamental because it shows how proportional our senses are. It tells us that our ability to detect a change, what we call the just noticeable difference, isn't a fixed number.
It's relative.
It's relative to the initial intensity of that stimulus.
So the classic example, if you're holding a 10-pound weight, adding 1 more pound is obvious. That's a 10% change.
Right. But now if you're bench pressing 300 pounds, adding that same 1 pound is completely imperceptible.
You wouldn't notice a thing.
Not a thing. You'd probably need to add 30 pounds to notice to keep that same ratio. And the crucial insight here is that all our sensory inputs operate within these proportional, measurable, and constrained limits.
Whereas a machine can be built to detect tiny arbitrary changes instantly.
Exactly. It immediately sets the stage for a divergence.
So human sensation is proportional, it's constrained, but human perception, that's dynamic and constructive. Let's move to that interpretive step, how we take those raw inputs and create these organized wholes. This brings us straight to Gestalt psychology.
Gestalt was a counter movement. It was a rejection of the idea that perception was just adding up a bunch of little atomic elements.
Right. They said the whole takes priority.
The whole is something else than the sum of its parts. That was their core adage.
It sounds a bit abstract, but it becomes really concrete when you look at the properties the brain uses. Let's start with reification. I love this one.
It's the constructive aspect of perception. Reification just means your mind is automatically filling in spatial information that simply isn't there in the stimulus.
Like the Knizia illusion.
The Knizia illusion is the perfect example. You have those three Pac-Man-like shapes on the page.
And you just see a bright white triangle in the middle?
You see it instantly, even though no lines define its edges. Your visual system is literally projecting that triangle into existence. A DNN doesn't do that. It just sees three partial circles.
It doesn't infer the hidden geometry.
Not at all. And then you have something like multistability.
The flipping images.
Yeah, the flipping images, like the Necker cube or the Rubin vase that flips between a vase and two faces. The image on your retina isn't changing at all.
But your mind is popping between two totally different interpretations.
Right. It proves the brain demands a single clear percept, even when the input is ambiguous.
And the third one, invariance, is maybe the most impressive feat we just take for granted.
It's incredible. It's the ability to recognize an object regardless of its scale, its rotation, its location, even if it's a bit deformed.
A chair is a chair, whether it's upside down or drawn in a child's scribble.
Exactly. That deep, immediate abstraction of shape is what lets us navigate a dynamic world.
And this whole demand for structure is codified in the Gestalt principles of grouping. They're all governed by this law of pregnance.
Which is just a fancy way of saying we have a bias toward simplicity and order.
Let's hit the key grouping laws, because these are like the hardwired rules of human perception.
Okay, so take the law of closure. This is the brain's willingness to just ignore gaps and see incomplete figures as whole shapes.
It's why the IBM logo works.
Totally. Those are just a bunch of horizontal bars, but you instantly read the whole letters I, B, and M.
Or the law of proximity. If things are close together, we see them as a group.
Right. A field of dots becomes columns or rows, depending on how you space them.
And then there's similarity.
If objects share a characteristic, color, shape, whatever, we group them together. It's a crucial first step in just segmenting a scene.
And finally, continuity, which is how we handle overlapping objects.
We see two intersecting fishing poles, not four separate line segments meeting at a cross. Our mind prefers the single, uninterrupted entity.
These laws really explain why our perception feels so stable and robust.
They do. And now, when we turn to the machines, we see that while they achieve this amazing statistical accuracy, they utterly fail to adhere to these behavioral rules we just laid out.
So let's transition there to the machine's blind spots. The first big behavioral gap is just opacity.
The black box problem.
Yeah, if we can't look inside, we can't claim it's a model of the brain.
That's right. The problem isn't the simple units that make up the network. It's the millions of layers and connections. The function is emergent and, well, it's largely impenetrable.
So we can't get a mechanistic explanation for why it made a decision.
We can't. We get these saliency maps or layer activations, but they don't give you a human understandable reason.
So we're left with this powerful statistical model that gives us the right answer 99% of the time, but we don't know the logic.
We don't. And that lack of logic seems directly linked to the next huge behavioral difference. The shape versus texture bias.
This is a profound one.
It really is. Humans, because of those Gestalt principles like invariance, we have a strong inductive bias toward classifying objects based on their global shape.
We prioritize the 3D structure.
We do. And what do the machines prioritize?
Texture.
Texture. They show an overwhelming texture bias, sometimes 80% of the time or more. Researchers showed this with what they called Q-conflict stimuli.
All right, remind us of that test.
It's where you take the shape of one object, say a sofa, and you fill it with the texture of a completely different object, like an elephant's hide.
So a human sees that and
Immediately says sofa. We completely disregard the texture cue.
But the machine, which relies on all those local high-frequency textural features, says
It overwhelmingly classifies it as an elephant.
wow.
It shows that despite being trained on billions of images, the DNN hasn't learned the same organizing principle. It hasn't learned the priority of global shape. It just took the shortcut.
That is a fundamental divergence. But I think the most unsettling failure mode has to be the adversarial examples. This is where the machine just acts completely irrationally.
It's the ultimate proof that the feature spaces they use are just fundamentally different from ours.
So you take an image that's correctly classified.
Correct. And then you add a tiny, almost imperceptible perturbation. It's just noise, but it's carefully mathematically optimized noise.
And that noise just flips the classification completely. The source gave that Crocodile Conjecture example.
It's wild. You take an image of a banana, add this invisible noise, and the DNN suddenly classifies it with 99.9% confidence as an African crocodile. The confidence is high, but the result is
Utterly meaningless.
to a human, yes.
So why can't we just say humans can be fooled too? We have visual illusions.
That's the key distinction. Visual illusions, or images that are just hard to see, are not the same thing as a proper adversarial example. A proper one relies on tiny, general perturbations.
Right.
There is no known, comparable, generalized, imperceptible perturbation that can consistently make a human misclassify a high-level object like a cat as a crocodile. It just shows the machine is optimizing for features that are irrelevant or maybe even dangerous in the real world.
And if that wasn't enough, there's also the 3D robustness gap.
Yeah.
It's not just about invisible noise, it's also about perspective.
Yes. Researchers found they could take a physical object, like a toy bus or a warplane, and just change the camera angle to a very specific, unusual viewpoint.
And the DNNs accuracy would just plummet.
They optimized for these adversarial viewpoints, and for complex objects, accuracy could drop below 20%. It would confidently mislabel the object as something totally unrelated.
But the critical point here is that for a human observer, these viewpoints were totally effortless.
Effortless. We immediately recognize the object regardless of the angle, which, again, is that core Gestalt principle of invariance in action.
It really creates this compelling argument. The machine has achieved computational efficiency, but not representational alignment with how we think.
They're solving the same problem-object recognition, but they are using entirely different algorithms to get there.
So we've tracked the machine's failures where humans excel. Now let's flip the script. Let's look at a stunning failure in the human visual system that helps us understand why our system works the way it does. Prosopagnosia.
Face blindness. It's a fascinating disorder. It's the impaired ability to recognize familiar faces, sometimes even your own.
While other visual abilities are totally fine?
Exactly. And the prevalence is surprisingly high, maybe 2.5% of the population.
So what does face blindness tell us about the normal human visual system?
It proves that the brain has a dedicated, specialized system for recognizing faces. This system, largely in the Fusiform Gyrus, operates holistically.
So it's not looking at a nose, then eyes, then a mouth.
No. It processes the face as a single, unified pattern, a whole template.
So if that holistic system fails, what are people like Brad Pitt or Stephen Fry forced to do?
They have to fall back on piecemeal, feature-by-feature strategies.
The kind of thing a machine might do.
Exactly. They look for secondary clues. Hair color, clothing style, the sound of a voice, a person's gait. They're using an object recognition system for a task that the brain optimized for holistic processing.
And the result is that the task becomes incredibly difficult and unreliable.
It's the perfect counterpoint. We see the cost of losing the holistic system in humans, and we see the cost of the lack of a holistic system in DNNs.
Which brings us to a really compelling synthesis here. We've basically found a double dissociation of performance.
That's a great way to put it.
Humans fail with prosopagnosia, where the system is holistic and specialized. Machines fail with texture bias and adversarial views, where the system is feature-based and statistical.
That double dissociation suggests you could, in theory, create a massive data set of images that humans get right and DNNs fail on, and vice versa.
It's the clearest evidence that they are not modeling our core object recognition behavior.
For now, at least.
Right, for now. We have to acknowledge the pace of change. This assessment is just a snapshot in time.
That context is vital. The failure to train one specific network, like an early ResNet, to be robust. Well, it proves nothing about the whole class of networks. Success is always a proof of concept. Failure is just proof of difficulty.
And modern architectures, like transformers, might be starting to narrow these gaps.
They might be, especially as researchers build in things like adversarial training to explicitly make them more robust. So if that behavioral gap is closing, does that mean the difference between human and artificial sight is just a matter of scale and better data? Is the brain just a very big, very well-trained DNN?
And that leads us to the final, and I think most provocative thought. It distinguishes between computation and implementation.
Okay.
Computationally, the classic argument holds. Any process the human brain computes, which uses recurrent loops, can also be computed by a deep feed-forward network, like a standard DNN.
So there's no fundamental computational advantage to having a brain?
Computationally, no. So the question becomes, if they are equivalent, why did evolution select for this messy, complex, recurrent biological system?
And the difference is implementation.
The difference is implementation. Recurrent loops in the brain where output feeds back into the input, They provide massive implementational advantages for a biological system under intense resource constraints.
Constraints like what?
Energy, space, biological latency. Recurrence lets the brain reuse the same limited number of neurons and synapses over and over again for different operations, which saves a huge amount of resources.
It drastically reduces the number of components you need, it saves memory space, and critically, it optimizes for energy efficiency. The brain runs on the power of a dim light bulb.
I see. So the machine uses millions of connections running forward to approximate a function, but it consumes massive amounts of power.
While the brain uses fewer components in recurrence to do the same thing, but efficiently.
Yeah.
Our robustness, our bias toward global shape, our use of Gestalt principles, they might not be signs of superior computing power. They might just be the evolutionary result of optimizing how the computation is performed under biological constraints.
The human visual system had to be energy efficient and compact.
The DNN just had to be accurate.
That is a staggering thought. That the differences we're tracking are just byproducts of an optimization problem solved under vastly different constraints.
It's a compelling angle for future research, that's for sure.
Well, thank you for guiding us through the nature of seeing, both human and artificial.
It was a pleasure.
And to you, the listener, we hope this deep dive into the difference between calculation and perception gives you something truly new to chew on. We'll see you next time.